Hi there, welcome to episode 2 of the Geology 101 video series. I'm geology professor Shawn Willsey, and this video series is for physical geology, Geology 101. It's aimed for people who've maybe had geology in the past but want a little bit of a refresher, possibly people that are currently enrolled in a Geology 101 course or learning similar content, or maybe you're brand new to geology and just want to start with the basics. But either way, happy to have you on board here. This course and this lecture series is modeled after my college course. The only thing that's a little bit different is this obviously doesn't have the in-person lab and field trip component. But nonetheless, you can supplement these videos with some of the other videos on my YouTube channel, particularly the Rock and Mineral series, but also by finding key videos that might relate to some of the content we have here. So thanks again for joining me. Again, this is episode 2, where we're going to introduce the concept or theory of plate tectonics. That'll probably take a couple of additional episodes, but let's go ahead and get started. So in episode 1, we learned about the interior of the Earth, the different layers that make up our planet. And today what we're going to do is look at a fundamental and unifying theory in geology. Now, a scientific theory is something that's incredibly robust. It has passed numerous, countless tests and experiments, and it's validated. It's something that works. Doesn't mean we know everything about how it works, but it works. And so it's a little different than the way we often refer to the term theory maybe in everyday society. So it's a little bit different than that. So let's go ahead and get started here. We'll learn more about some of these graphics as we go. We'll learn about this person here, this individual, Alfred Wegener, as well. So, turn my light back on. Okay, so the idea of plate tectonics really began with this more broad concept known as continental drift. And the interesting thing about plate tectonics is it's really quite a new theory or a new idea in geology. Only within the last maybe 60 years or so has plate tectonics really revolutionized the way we think about Earth's processes. So Alfred Wegener was a German meteorologist, and he wasn't necessarily the first one, but he was among the first that put together a lot of the ideas, looked at some observations, and came up with this idea known as continental drift, where all the continents were once joined into a single landmass, a supercontinent called Pangaea. And he had plenty of evidence for this line of thinking. There's the obvious sort of fit of the continents. If you look at especially like South America and Africa, and you treat them like jigsaw puzzle pieces, there's sort of a natural fit between the two, especially if you don't look at the coastlines of continents, but actually the outer margins, or what we call the continental shelves, where the ocean really drops off to deeper levels, or that surrounds those coastlines or those continents. Those somewhat fit amongst many of the continents. There was evidence in the form of fossils that we'll talk about here in a second, glaciers, similar mountain ranges, and then rock sequences. So it was a pretty bold idea at the time, and you have to go back to the line of thinking that prevailed at that time, which was that there wasn't a lot of dynamic processes. There was obviously things we could observe, but the continents were thought to be quite rigid. The idea that there was movement on such a huge global scale involving what we find out later is like the Earth's crust and upper mantle, what we call the lithosphere, was a pretty bold claim. So let's look at a fun little animation here that will explain this in a little bit of detail. And this is one from it's no longer available as much as it used to be, but from a publisher. Pearson had this put together, and I used to use this in class quite a bit. So this is the idea he proposed, that the continents were stuck together into this single supercontinent called Pangaea. You can probably make out most of the outlines of the continents there: North America, South America, Africa. This is Antarctica, Australia, India, Arabia, and Europe, Asia, and Greenland here. So more or less put together. And this animation is highly simplified. It's a little bit cartoonish, but it conveys the general point. And what he proposed then is what this single supercontinent had actually split apart over time, eventually separating into mainly two big continents or land masses, one known as Laurasia, the northern hemisphere continents, and one called Gondwanaland, mainly the southern hemisphere continents, and that these, of course, drifted apart over time. Now, he didn't know the time frame for these, But he did postulate that these continents had separated over some period of time. So you can kind of see where things are moving here and just kind of following along. So here we are about 50 million years ago. The map's starting to take shape, looking similar to what we see today. India has not yet docked with Asia at this point. There's a few little differences here. Australia is continuing to move further north. And then we arrive at our present day map, which looks more or less something like this. So this is the map of the Earth that you were born with, and this is the map of the Earth that you'll likely die with. No discernible changes take place within a human lifetime. But because today we now know that not just the continents, but the plates are moving, and we'll get to that here in a bit, and we know which direction they're moving and the rates or speeds at which they're moving, a fun thing to do is actually plug this all into a computer and model what the future map of the world might look like. And so I'll click this one more time, and this will show you what the map of the world might look like in another 50 or so million years. And not a lot of differences there, but there are some subtle things there that are somewhat important. And so you can see that the continents, let's go back a little bit here and then run it one more time. So one thing you can see is the Atlantic Ocean getting wider. North and South America drift further to the west. So the Atlantic Ocean and the Atlantic Basin gets larger. So your flights from the US to Europe are just going to take longer in the future because it's a bigger distance, takes more fuel, it'll be more expensive. What are some other subtle features we saw here in that animation? Well, Australia is going to continue to move north. It's been moving north for about 100 or so million years, and it's continued to move north. Let's talk for a second. Australia is a good point to pause and talk about how plate tectonics affects climate and how climate dictates ecosystems, plants and animals. So Australia today, as you probably know, sits more or less straddling the tropics here. And so it sits at a fairly low latitude. The interior of Australia, as you probably well know, is quite hot and is mostly a desert. So there's kangaroos jumping around and dingoes. Of course, along the coastline in places, it's maybe a little bit more a moderate climate. And the north coast of Australia is more of like a rainforest or tropical climate. But much of Australia's interior is a desert. And mainly it's a desert because of the latitude it sits at. The world's deserts more or less coincide with this, 25 to 40 degree, either north or south latitude. So the single greatest control on climate is latitude, your position north and south on the globe. Notice where Australia is likely to be in 50 million years. It's going to be more or less straddling the equator. And so think about the climates that we have in and along the equator in Central Africa, in the Amazon basin of South America. These are the rainforests. These are places where there is exceptionally high rainfall rates. Weathering is very intense and enhanced. There's thick soils, thick canopies of vegetation, and an entire ecosystem of animals that thrive in that type of climate. So just imagine how different Australia is going to look in 50 million years when it moves from this subtropical location to being right over the equator, and how different its plant and animal communities might look at that time. So again, plate tectonics is important because it's a driver of climate and biology or ecosystems in any given area. One other thing I noticed here as we ran the animation is India continuing to plow northward. Of course, most of you probably know that in between India and Asia is the world's largest mountain range, the Himalayas, including Mount Everest. So this animation, if it's to be believed, implies that if India continues to plow northward into Asia, that those mountains that are there as a result of that collision will continue to be uplifted. And so Mount Everest isn't getting any smaller anytime soon as that collision, which began several million years ago, continues into the future. And then maybe the last most notable thing on this fun little animation that you might have seen here, if we go back just a little bit to again, the present map, watch what's happening over here on the west coast of North America. Do you see it? So there was a piece of North America that's been shifted off the margin of the continent and transported to the north or northwest. And this is Baja California and coastal California, everything west of the San Andreas Fault. Of course, the big misnomer urban legend you hear is that California is going to fall into the ocean during the next big earthquake. Well, that's not true, because as we learned in episode 1, California, along with Baja California, is made out of continental crust, and continental crust is buoyant. It doesn't sink, it doesn't subduct. And so the real end result here is that this part of the continent, everything west of the San Andreas Fault, is actually going to move off to the northwest. At some point possibly become an island, and then eventually collide with and dock with Alaska and maybe even a little bit of Canada here. And so it'll be very different there as well. The nice sort of Mediterranean climate that Southern California experiences now will have to give way to a much colder and wetter type of climate in the future. So this is the idea that Wegener was putting forth. This idea of continental drift was what he named it. And he had some good evidence. So there's some of the fossil evidence he had. So we find the exact same species of some fossils on different continents. So you can see sort of the distribution of a few key fossils here. This fern Glossopteris is found on 5 different continents. You can see some of these other fossils as well. And a biologist will tell you that when you isolate and separate a species and allow evolution and time to take place, those will eventually evolve into very distinct and different species. They're in different habitats. Over time, they will not mate, and so they will become different species. They'll develop different traits and characteristics depending on their environmental pressures. And so having identical species of organisms that can't cross the ocean doesn't make any sense. But when you reconstruct the continents and consider them as a joined landmass, then it makes perfect sense. And again, this was some of the evidence that Wegener was using to put forth his idea, this idea of continental drift. There's some evidence for glaciers as well. And so when we look at the distribution from glacial evidence, and you might ask, well, what evidence do glaciers give us? Well, glaciers can give us both erosional and depositional evidence. So there's both the glacier advancing across a landscape, scouring it with ice, leaving polish marks and scratch marks on the landscape. But also, as the glacier reaches lower elevations and its terminus, it'll deposit and drop a lot of sediment. And so there's a number of ways in which glaciers can leave evidence of their existence. And so when we look at the evidence of glaciers in the southern hemisphere especially, and maybe looking back a few, 100 plus 200 million years ago, we see that there's glacial evidence in places that don't make sense today. Australia has no glaciers today, and yet there is distinct evidence that it once had glaciers on its southern margin. Glaciers in Antarctica, that's okay. We have glaciers there today, so evidence of ancient glaciers, no problem there. But again, the distribution and the location of some of this evidence for glacial activity doesn't make much sense until you reconstruct the continents in their best fit scenario, and then it becomes one common polar ice cap that's glaciating these land masses all at the same time. So there's some of the evidence in the form of glaciers. There was evidence in the form of just rock types and mountain ranges. So for example, if I took you on a field trip into the northeastern U.S., maybe Pennsylvania, New England area, and we look at the rocks and we look at the fossils and the history of those rocks, and then we fly across the Atlantic to the UK or maybe parts of Scandinavia, Norway, we can effectively see the exact same rock types, sequences, layers of rock stacked on top of each other, exact same fossils. And again, that doesn't make much sense with separated continents, but when the continents are joined and that becomes a singular connected belt of rocks and or mountain ranges, it makes much more sense. So today we can look at the evidence for plate tectonics and continental drift and say, well, yeah, like this, seems pretty obvious. It seems like a slam dunk. But you have to remember 100 plus years ago at the time and the thought process, the dogma that existed at the time was very different. And so ultimately what happened with this idea that Wegener put together? Well, it was flat out rejected by the scientific community. And the main problem that was his his idea faced was there wasn't really a mechanism. When he was really asked and forced to come up with a mechanism or a way in which the continents could move, which seemed preposterous at the time. How do these huge continents, which must weigh a tremendous amount, how do they just sort of plow across the face of the earth and move? What's pushing them or what's pulling them? And he really didn't have a good answer to that. He just knew that the evidence was very much pointing towards continents had once been together and had drifted apart, but he couldn't figure out what the mechanism was. So the idea pretty much drifted, pun intended, drifted away at that time, wasn't really considered part of the scientific thought process at that moment. And what happened to our good friend Alfred Wegener? Well, tragically, in 1930, he's on an expedition in Greenland, and he's out doing research. As the story goes, he gets separated from base camp during an absolute blizzard, can't find his way back to base camp, and dies of exposure. So another case, and we have many of these in science, of an innovative thinker that was ahead of his time. He was onto an idea that would later be validated, but he died not being able to see that validation come to pass. And so, but we still revere and champion Alfred Wegener, along with many other geologists who helped us move forward with our thought process. So what happened next was the idea kind of went on the back burner. A few people kind of looked at it, but no one really ran with it, and no one really went after a lot of evidence for the most part. And if we fast forward the timeline and the story here to post World War II, wars are always a good way for technology to move forward. And one of the big advents coming out of World War II was we had used sonar, sound waves in the ocean, to look for submarines, but also to map the seafloor. If you're going to creep around in submarines out here in the ocean, you need to make sure you know what the topography is like, so you don't run into a underwater mountain or something like that. And so in the course of doing research post World War II in the 50s and early 60s, we realized that the Atlantic Ocean and other ocean basins as well had this impressive underwater mountain chain that ran for literally tens of thousands of miles up and down the ocean basin. So right where you might think, if the ocean basin's a big bowl, you'd expect it to be deepest in the middle, we actually found that it was shallower there than we expected, and that the mountain range had some interesting geometry to it. It also had high heat flow, so the rocks at the bottom of the ocean were transmitting and carrying more heat than adjacent areas closer to the continents. And these areas were sometimes volcanically active. They produced earthquakes quite frequently. And then later, as we developed the abilities to date rocks, we found that the youngest rocks were right there at the center, right on the crest of these underwater mountain ranges, and that the oceans got older as we moved away and towards the continent. So this really created a huge dynamic in geology, this new data coming in. What does it mean? How can we explain it? And this helped us dust off some of those ideas from Wegener and look at them in light of some of this new data. At about the same time, we started studying the magnetic field of the Earth and looking at how that's recorded in Earth's rocks. And so just a real quick primer on the Earth's magnetic field and how that works. And so if you're at the equator here, the Earth generates a magnetic field like a big bar magnet. So if you're at the magnetic equator, you can look at this little diagram here, your compass needle will be oriented, it will point north, as it should, but it'll also have, if you look at my little diagram here with me in it, if this is the compass needle here, this pen I'm holding, if I'm at the magnetic equator, my magnetic needle here will be oriented horizontally. It'll still point north, but it's going to be parallel to the Earth's surface. But as I move further north, so let's say I leave the magnetic equator area, and let's say I'm now in Florida or Texas, now it'll still point north, but it's going to have an inclination or tilt to it. Now that magnetic needle, if it's allowed to rotate in three-dimensional space, it's actually going to have a little bit of a tilt to it, still pointing to the north. And if I continue moving further north, that needle will continue to increase its orientation, getting steeper and steeper until I reach the magnetic pole, at which point my little magnetic needle will be oriented vertically. And so what this tells us then is that we can use the orientation of magnetic materials that will be aligned with the Earth's magnetic field. We can use that as a proxy for latitude, how far north or south of the equator you are. And so when we started applying this to rocks, recognizing that especially volcanic rocks like basalt have high amounts of iron in them, there's minerals that are naturally magnetic. So as they flow out as lava flows, all that stuff's kind of getting moved around. But once that lava stops moving, those minerals, before it becomes solidified, will orient themselves with the magnetic field that exists at that time. And what we found then is that it looked like some of the continents that wherever they are today, that they had quote unquote drifted over time, or they were once in a different location. So for example, if we go to a place like Ecuador, which sits on the equator today, and we look at rocks 10, 15, 20, 30 million years ago, we find that those rocks show signatures, magnetic signatures of that location in Ecuador not being at the magnetic equator, but it being some higher latitude, some distance away from the equator. And so all of this together was really compelling evidence for that, yes, the continents actually have moved and still move. And so all this was being put together. It was a very exciting time in geology because the data and the discoveries were coming fast and furious. And slowly but surely, it was filling in the gaps of knowledge that existed from back in Wegener's time. The other thing that came about during the study of the Earth's magnetic field is that the Earth's magnetic field reverses itself from time to time. So every day, your whole life, the Earth's magnetic pole is the North Pole. If you take out your crackerjack compass and point it and hold it, that needle will point north. It did it on the day you were born, and it undoubtedly will do it on the day you leave this Earth. But what's interesting is that magnetic signature sometimes flip-flops. And so sometimes, and we don't understand all the intricacies of this. This is one of the big holes in our knowledge, is exactly what controls Earth's magnetic reversals, how often they occur, and some of those dynamics. But what you can see here on this upper right sort of candy stripe looking graph is a record going back about 4.5 million years of Earth's magnetism. So normal magnetism is what we call North Pole magnetism, taking your compass out and your compass points north. Reverse magnetism would be taking your compass out and the compass pointing south. And so you can see that over time it's flip-flopped, but there's not a real clear cyclicity or pattern in terms of the time component involved here. All we know is that it flips, and it seems to flip quite quickly within a few thousand years or so. So the time frame it takes for the magnetic pole to completely reverse itself seems to be fairly quick. And so let me show you one more animation here that will help us understand how this works. And so it's a little bit fuzzy, I apologize for that. But if this is our ocean basin where the plates spread apart, which we'll get to in a minute. So this is where new ocean rock is created as we have volcanoes erupting on the seafloor. So if the North Pole is the magnetic pole at the time these volcanoes erupt, then their little minerals will record North Pole magnetism. But if it flips to South Pole magnetism and the volcanoes keep erupting on the seafloor, then that little swath there of rock will have minerals that record South Pole magnetism. And then at some point in the future, it flips again. And when it flips again, there we go, North Pole magnetism. These rocks record North Pole being the magnetic pole. So you can see that essentially the ocean basins, which continue to spread and open, are kind of like a tape recorder. And they record on either side of the plate boundary where the spreading's taking place, this flip-flopping of the poles, north to south. And this can only be explained by having the ocean basins opening up as this lava is erupting here on the seafloor. So another huge piece of evidence that helped to validate and cement the plate tectonic idea a little more firmly, this idea of not just paleomagnetism, but these magnetic reversals. And so with that, as we moved into the late 60s, plate tectonics had become a better accepted and eventually a completely widely accepted theory, scientific theory. It combined Wegener's early ideas and observations of continental drift with some of the advances that came after World War II that involved seafloor spreading. It explains, for the most part, where, I don't know, 90% of all the Earth's volcanoes are. It explains 90% of all our earthquakes. It explains many of our mountain ranges. Many of Earth's dynamic features and processes are very well explained by plate tectonic theory. That's why it's considered a unifying theory. It actually explains lots of observations from lots of different fields and gives them a common framework that ties them together. So you can see that our Earth is divided up into a series of plates, what we call tectonic plates. Some are large, like the North American plate's quite large. The Pacific plate is large as well, but the way this map projection is, it looks maybe a little bit smaller than it actually is. Some plates are small, like the Juan de Fuca plate, which sits off the coast of Washington, Oregon, and Northern California, as well as southern British Columbia. Some plates are made of just ocean basin, like the Pacific plate for the most part. Other plates are made of both continents and oceans. But all the plates are moving in different directions, and the action tends to be along these boundaries. And that tends to be where the bulk of Earth's most dynamic processes occur. So if you think about earthquakes, you think maybe of Southern California or Japan or Indonesia or the Philippines or the west coast of South America. Those are all earthquake-prone regions, and they coincide nicely with these plate boundaries. If you think about volcanoes, you might think of Iceland. You might think about the Andes, the Cascades, Japan, the Aleutian Islands. You might also think about Hawaii, so we'll have to explain that one. That one doesn't line up real well. But most of the Earth's volcanoes, New Zealand, can be explained there. So what we're going to do in our next couple of episodes is dive into these specific plate boundaries, look at the types of plate boundaries, look at the processes that govern at these plate boundaries, and what sort of features exist there. And this, I can't emphasize enough how incredibly important it is to have a good, solid, basic but fundamental understanding of plate tectonics as you move forward in your geologic studies, because this undoubtedly is what forms the foundation of our knowledge. So you can't really understand earthquakes well without having the concepts of plate tectonics in your back pocket. Oh, you can't understand volcanoes as well unless you understand how it relates to plate tectonics. So that's our first episode. This is episode 2, but it's our first episode, probably a 3-parter, I'm guessing, in covering plate tectonics. So I hope you have enjoyed this. Please like, share, subscribe, and look for the next part coming up soon. I'll get these out as quickly as I can, but sometimes it might take a week or so for me to prepare each lecture episode. Feel free to supplement these lectures with any other resources you find. You can obviously Google any number of terms and find other resources out there that might help you with your study and understanding. So hope that was helpful. Thank you so much for your time, and take care.